So the third case of electromagnetism is the force acting on a moving charge in a uniform magnetic field. So let's say you have this proton, positive Q, entering into this magnetic field. And this magnetic field, can you see, is out of the plane of paper. Now, the charge, as it moves in your field, will experience a force. Now, why? The reason is a moving charge, according to Maxwell, generates a magnetic field. So that means you can treat this charge as a small magnet. So therefore, a small magnet moving in a magnetic field will surely experience a force. So what is the formula for the force? The formula for the magnetic force on a charge moving perpendicular to the field is F equals to BQV. So which means to say we must assume, we must assume that the charge is entering perpendicular to the field. Let me just write nicely. Okay. Let's say positive charge enters perpendicular to the field. So when it's perpendicular to the field, then you will experience a force. Now, if the charge enters at an angle to the field, so let's say this is the B, and then the charge enters at the angle V, angle theta with speed V to the field, then your force will be F equals to BQV sine theta. That means you must find the component of the speed which is perpendicular to the field. Then you get maximum force. So this would mean as well, if the charge is entering parallel to the field, your theta will be 0, right? So sine 0 will be 0. So therefore, if a charge is entering parallel to the field, it will have no force. Alright, it's because of the direction of the magnetic field generated by the moving charge. So when the charge is moving this way, then its magnetic field will be parallel to the field. That's why it experiences a force. But if it enters parallel to the field, then the magnetic field is perpendicular to the field, external field, so there's no force. So therefore, you must remember something. From this formula, we can see two things. Number one, if the charge is stationary in the magnetic field, there's no force. That means only a moving charge has a magnetic field. A stationary charge has no magnetic field. So therefore, when V is 0, no force. And not only must it be moving, it must also be moving perpendicular to the field in order to get a force. If it's moving at an angle to the field, then we have to resolve the velocity into two components: parallel to the field, which will not give you any force; perpendicular to the field, which will give you the force. So when the charge enters perpendicular to the field, example, let's start from here, enters perpendicular to the field, what will happen to its motion? That's the question. So we always say that it will move in a circular motion in the direction of the force. So let's predict the force first. The force can be predicted using Fleming's left-hand rule as well, the direction of the force. So you can still use a Fleming's left-hand rule where the pointer represents the field, so you can point to your right. But you know the middle finger, which is supposed to represent the current? So that actually represents conventional current. Now, conventional current is assumed to follow the flow of positive charge. So if this is a positive charge moving upwards, so a conventional current is taken to be upwards. So you can take your middle finger and point up. So you take your pointer finger, point to your right, middle finger point up, alright, which is like this, and then your force will be into the plane of paper. Okay, so when the force is into the plane of paper, what will happen is this charge will enter into the plane of paper. So it's hard to see. Let's look from here. So this one, the field is out of the paper, so you take your pointer finger, point out of the paper. Positive charge move from left to right, so therefore conventional current is also left to right. So the force is downwards. So it will enter and move in a circular path. Now, why will it be a circular path? Some people say, how do I know whether it's a circular path or whether I know it is just a curve like a projectile motion, a parabolic curve? Now, the difference between circular motion and parabolic curve. In a parabolic motion, example, when you learn in AS about the projectile motion, if you project an object with speed v at the angle theta, so what happens is it undergoes a projectile motion, right? So what gives the object a projectile motion is that at every point along the path, the acceleration is always in the same direction, which means to say your acceleration, which is g, is here right now. So even when you reach another point here, your acceleration, which is g, is always still downwards, it never changes. But your velocity is the one that changes. You will always be tangent to the curve. So you reach this point, velocity tangent to the curve, but acceleration still downwards. So if your acceleration never changes direction, only your velocity changes direction, you will get a projectile motion. To get a circular motion, example, let's say you have a string, you tie a stone to the string and then it moves in a circle. The direction of the velocity will always be tangent to the circle, and the acceleration will always be towards the center. Why? Because of centripetal acceleration, right? So what you will notice is the velocity will change, the acceleration will also change direction to maintain 90 degrees with your velocity. So when that happens, you will get a circular motion. So velocity changes direction, acceleration maintains 90 degrees to your velocity. So that's how we predict lah. So when we go back to that previous diagram, when we look at this diagram again, you will see that when the object comes into the field, the force is downwards. So that means, can you see that the force which is your acceleration will be 90 degrees to your velocity right now. So when it curves, your velocity will also change direction tangent to the curve, but the force will maintain a 90 degrees. Now why will it maintain 90 degrees? If you use a Fleming's left hand rule, you'll notice that when you rotate your middle finger to represent the direction of the velocity, the thumb will maintain 90 degrees and rotate as well. So it always maintains a 90 degrees. So therefore it gives you a circular motion, because the acceleration which comes from the force is always 90 degrees to the velocity. Okay, so because it is a circular motion, we can have this formula. So just now we said that the force is F equals to BQV if it enters perpendicular to the field, which is in this case lah. So the magnetic force, which is FB, will now become your centripetal force because it's moving in a circle. So the equation for a charge moving in a circle in a magnetic field is always given by this equation, FB equals FC. So you get BQV equals to mv squared over r. So you cancel one of the v and your r equals to mv over bq. That means the radius of the circle that you're going to make will depend on the velocity, the mass, the flux density, and the charge, which is logical. Think about it. If you're moving very fast, that means your inertia is high. So it's harder to turn, right? So your radius is bigger. That means you take a very big turn, so your radius is bigger. But if the flux density is high or the charge is high, then the force is high, right? Because B is high, Q is high, or force is high. So bigger force means you will make a tighter turn. That's why your radius is smaller. So whenever a charge moves perpendicular to the field, definitely it will move in a circle. And if it moves in a circle, we definitely can use this equation. So you must remember to use this equation. Okay, so now, what happens if the charge enters at an angle to the field, like in this case? Now you notice that here they're using an electron. So when you use electron, it's very important to remember to use Fleming's left hand rule. If the electron is moving, let's say, upwards here, we must take the conventional current to be downwards. It must be opposite. So when you use a Fleming's left hand rule, the middle finger must point down, not up. Because why? The Fleming's left hand rule, the middle finger represents conventional current, which is assumed to be the flow of positive charge. So if negative charge electron moves up, then your conventional current is down. So you use the Fleming's left hand rule, the field is to the right. Conventional current, now what we do is this: we resolve the velocity to two components, parallel to the field, which is to the right, horizontal to the right, and vertically upwards, right now. So the one horizontal will not give you any force, but the vertical, if your velocity is upwards, because it's an electron, you must take conventional current downwards. So if you use a Fleming's left hand rule, pointer finger to your right, current downwards, you will notice that the force is out of the plane of paper. So what it means is, it will come in, it will turn out of the paper. It will move in a circle out of the paper. But don't forget, you still have a v cos theta in front here. That means if this is theta, you still have v cos theta forward. V sin theta gives you the force, which makes you move in a circle. But v cos theta still causes you to move forward. So what will happen is, as you move in a circle, you will also move forward. That's why you get a helical path. So they asked this in the past year before. They said, describe the path if it enters an angle to the field. So you say it moves in a helical path, or you say the path is a helix, which means to say it is moving in a circle and moving forward. So it's like a spring. So the spring is like a helical path. So I'm not saying that horizontal you have a force, but I'm just saying that because horizontal you have a velocity and there are no forces acting horizontally to slow it down, so you continue to move forward. So you move forward, the force is acting to make it move in a circle out of the plane of paper, but then your horizontal velocity will be unchanged, so you continue to move forward.